Well, good morning. It's 8:31 on Tuesday, the 9th of July, 2019. This is supposed to be differential equations, and unfortunately I'm the only one in the room right now, so I'll go and get started. I would normally be asking if there were questions, but since there's no one here to ask questions, I'll just get started. If and when some people show up, if there are any announcements, I'll make them. I can't think of anything that's too crucial right now. So, where we left off last time, we're in Chapter 2, First Order Differential Equations, and 2.6 is a numerical method. There are many numerical methods, and that's why they appropriately named this one a numerical method. And this is a fairly simple one, sort of straightforward, and it's basically the linearization method, okay? We will later call it Euler's method, okay? In fact, just in a little bit. So what we had was, where we left off last time, we had a differential equation like this. Let me get my pen set up. Yeah. Well, it's not taking. There we go. Y prime is equal to, oops. I know it's in here somewhere. There it is. Y prime is equal to 0.1 times the square root of y plus 0.4 x squared. Okay? And it had an initial condition, y of 2 is equal to 4. Okay. Now, there is our problem. Now, I think probably as we mentioned last time, this is not one we can use separation of variables. Too bad. It would be nice, but it's not workable. It's definitely not linear with that square root of y in there. Don't believe they could devise this in any way, shape, or form that would be an exact differential. And some of the other things we looked like, it's certainly not homogeneous or homogeneous. I don't think any technique we've had to date would work. In fact, I'm not sure that there is an analytical technique that would solve that differential equation. So what do? We try a numerical solution. Now, to do a numerical solution, obviously you have a real-life problem at hand, okay? And a real-life problem will have some sort of initial condition. Without that, you can't do a numerical solution because you have to have somewhere to start. And since there is an initial solution, initial value given, that is a good place to start. And we took this through the process, trying to find, there it is. I actually state in the book, the nonlinear differential equation of this initial value problem cannot be solved directly by any of the methods considered in sections 2, 4, and 5. Nevertheless, we can still find an approximate numerical solution for the unknown function y of x. Specifically, we wish to know the value at 2.5, y of 2.5, which is not too far from 2, okay, which is good, okay, because that means that we don't have a long way to go, so a numerical approximation probably will get us pretty close to what it'll be at 2.5. And this method we're going to use won't get us exactly. It would be just happenstance if it gave it exactly, but it will give it pretty close, okay? Now, what they do initially is since this is our y prime here, we know this y prime at the point 2, 4, you can plug in and see what you get. So y prime would then be, and this is what we did last time, okay, but just for reviewing it now, 0.1 times the square root of y, which is your 4, so that's times 2, plus 0.4 times x squared, well, x is 2, x squared then would be 4. Now, don't expect them to be like this one, well, there it is. Okay. Now, so what we have now is y prime is equal to 0.2 plus 1.6, which is 1.8. So there's your slope at that point. Okay? Exactly. We know that. That's the slope at that point. So now, what we do is see if we can come up with the equation for the tangent line at that point. Well, you got the slope, so the tangent line will be y minus y1, which is 4, is equal to the slope, which is 1.8, times x minus x1, which is 2. Okay? And that gives us y minus 4 is equal to 1.8x excuse me, minus 3.6. Okay? Add 4 to both sides, and what you get is y is equal to 1.8x plus 0.4. Okay? There is a linearization of the solution for this at that point. Okay? Now that's our best guess. And what they call this in the book is your L of x, the linearization as a function of x. Okay? And that's where we left off last time. This is called the linearization of y of x at the point when x is equal to 2, or at the point 2, 4. Okay. Now, that's all we got. We don't have a solution. We have this linearization. So let's approximate that, or use that to say, well, what would be the next value as long as you didn't get too far from there? Now, what does it mean not getting too far? Taking a very small increment of x. Okay? And what they suggested first is let's just go up by 0.1. Okay? So, if we increase the x by 0.1, then we're going to estimate a new y1 to be 1.8 times 2.1. Okay? What we're doing, we're going up the tangent line, not up the curve. We don't know what the curve is, but we know what the tangent line of that curve is, and as long as you're not too far from 2, that's going to be pretty close. If you've got a book and look at that, you see the picture of it there. At the point 2, 4, you see the tangent line is very, very, very close to the actual curve. Now, they knew the curve, we don't. Okay, but you see, our approximation is not going to be too bad. Okay. Okay. So it's 1.8x plus 0.4. Okay. All right. So let's figure out what that y1 would be. I don't have a calculator in here on me. Here's what I'm going to do. Yuck. Let me see if I can reduce this. That expands it. Will this reduce it? Let me see. Yes. That doesn't help me a lot. Let me go back. I don't have a calculator in here. I was hoping someone would be here with a calculator. So let's just do it. 1.8 times 2.1, and that would be 1.8, 16, forget about the point there, 36, so that would be 378. 3.78 plus 0.4, and that would be 3.82. Okay, that's our next one. The first one was, we knew it was 4. This is not going in the right direction. I must have messed up my multiplication here. I can't multiply. 1.8 times 2.1. 186. Oh, 0.4. I'm sorry, I did 0.04. Sorry. That's where my mistake is. Okay. My multiplication was all right. It's my adding was bad. Okay, that would be 4.18. Okay, 0.4, yeah, okay. 4.18. Yeah, that's going in the right direction. So that's our next guess, okay? So now we have an x1, y1. The x1 is 2.1, the y1 is 4.18. What do we do with that? We plug it back into our y prime, the thing we know. Y prime is equal to. Now what we're doing is guessing. That's pretty close to the point that we're interested in. So now let's see what the slope is at that point. So we're going to do 0.1 times the square root of y, which is 4.18, okay, plus 0.4 times 2.1 squared. Okay? Now, I'm not about to do that one in my head, nor am I going to work it out, though I know how to do that, take a square root of a number like that, but it's a real big pain in the neck. And to the rescue. Okay, here comes Nolan. You better have come right then, because I was running out of, let's see, today is... You got a haircut. Say again? You got a haircut. Probably more than one. I can't remember when I had one. I did get one at some point. Okay.
During the break?
I don't think so. Oh. No. I think you were asleep last week and didn't even notice it. I'm just kidding. No. I mean, no. All right. That's good. Present. Good. Okay. I'm especially glad to see you today. Yes. Because right at this point, I was needing a calculator. I had to do a multiplication on the board because I didn't know how to set up the thing now. And I was just about going to have to take a square root, and I sure didn't want to do that without a calculator. So, no, I'm glad to see you because I wanted you to be here. I'm sorry.
Sorry I'm late.
No problem.
I thought I set my alarm to like 7:30, but then I woke up and my dad was like, "Hey, what's going to be at school?" And I was like, it starts at 8:30. He's like, "Oh, it's 8:15." And I checked my phone and it said my alarm was set to 8:30. And I was like, "Oh, that's great."
Really good. So, well, I actually missed my alarm this morning too, so I know the feeling. Fortunately, my wife also didn't hear it, but she got up and went to the restroom, bathroom, so I heard her when she did that, and I looked and said, well, it's got to be close to time to get up. Looked at the clock and went, what? I just overslept for close to half an hour. So
you want me to do the square root of 418?
Yeah, well, do that whole thing here. 0.1 times the square root of 4.18. 2.18 plus 0.4 times 2.1 squared. And thank you so much for being here. Okay. Second?
I got 1.96.
1.96. That would be the slope there. See, earlier we had the slope of 1.8. And just to let you know whether things are looking good or not, you don't have the book with you. Here is the curve that the book somehow knew what the curve was. They used probably another more elegant package. We used the slope here of 1.8 initially. It got us a little bit further on to 2.1, and then we just calculated the new slope here. Where did we do it? No, there it is, of 1.96. And sure enough, just beyond that, it's getting steeper. So yeah, I'm not at all surprised that your slope there at 2.1 would be 1.96. And then you go through the process again, and use your linearization, which we have here, only this time you use 1.96 as the slope. Oh, no, we got to go back and get the new y-intercept for that new linearization. So what you do, say again?
Oh, never mind. That's 0.4.
Yeah.
I was just saying, if it was like, somehow you could like minus away, like, no.
Yeah. So what you would do then is, since this is the new slope, and these are your values, 2.1 and 4.18, the xy values, you go back and use your point slope formula, and this time is y minus 4.18 is equal to 1.96 times x minus 2.1. And figure out what the new y-intercept is. It won't be 0.4 again, it'll be something different. And then that's the new one you use for the next one. So it's a process that you use the previous information to come up with the new information, okay? And it should follow the curve, as the book shows here, closely, but it's certainly not going to be right on the money. Because this is curving up, every one of your slopes here is going to underestimate slightly what the next point is. So at the end, when you get to a 2.5, which is where we're wanting to go, you're going to be less than, but you're not going to be far off, okay? And this technique, and we're not going to take it any further, the book didn't even go this far, but this technique is called Euler's method. Now, I said initially that there weren't any announcements, or I wasn't going to make any announcements to an empty room, but I did want to make this one now that we've got a body in here. And it's not really an announcement, it's just a reminder. There is a paper in this course.
Yeah.
Okay. And I've gotten 2 in so far from this class of 6, so 1/3 of the people have turned them in. And we're getting close to the end of the term, okay? Especially for those people who might have 2 classes, which means 2 papers that might have added significance. Right, okay. All right.
Yeah, what I'm doing this weekend.
What's that? Yes, okay, good deal. I thought that's what you were doing last weekend, since you had such a long weekend.
Last weekend I went down to Auburn. I had to move and stuff.
You had what?
I had to go down to my apartment and get it ready.
Oh, I see, yeah. See, we're getting right near the end of the term. That should have been a reminder. Hey, I got 2 papers to do. Okay, but anyway, all right.
I get them done.
All right, good deal. I know you can.
I wrote a 10-page paper the night before it was due.
Okay, I don't want 10 pages, and I want it done a little more carefully than that, okay? All right. Okay. That said, let's move, but the reason I said about the papers, Euler's method, who in the world is Euler? That would be a possible paper topic. Or, how did he develop this method? How is it used? You know, something like this. There's lots of possibilities there.
Is this the guy that challenged his dad in the math competition or something?
No, that was Bernoulli. And he beat his dad in a math competition, and his dad kicked him out of the house. Okay, that was Daniel Bernoulli, I think. and his father was either Johann or Jock or something. But anyway, that family was pretty interesting too. So they would be a good topic. Euler, if I'm not mistaken, I may have this wrong. I always get Euler and Gauss crossed up for some reason. They're not really all that similar, except they're both really prolific writers. I mean, goodness gracious, the number of papers they produced in their lifetime were just unbelievable. And the way they advanced math in their lifetime was unbelievable. One of the two, when you mentioned his dad, I thought this is what you're going to bring up. His dad was basically a bookkeeper, an accountant, or something like that. I don't remember if it was for a city or for a company or something. And when he was like 5 years old, he was watching his dad work. He said, "Dad, you made a mistake here." And he had. He was that good at math. At five, or something, at very young age. It may have been like 8, but what's that?
That's still like dang.
Oh yeah, it's just absolutely amazing. And the reason I think it may be Euler, so it could be Gauss. It seems like Euler went blind in his later years, and he still produced papers because he did all the calculations in his head. And I couldn't correctly add earlier, on the board, so remarkable person. Okay. Gauss was also remarkable, but I think this was Euler, the one I'm describing now. But like I say, for some reason I get those two crossed up, their histories and that kind of stuff. I think it's that they were both such prolific producers of papers. I don't know how they did it, because if you put all their works together, it'd be volumes. Now, you produced a 10-page paper overnight with word processing and printers and all that kind of stuff. They did everything probably with ink and stylus type stuff, How? I don't know how they did it, but anyway, they did.
They were a lot smarter than we were, because we all rely on calculators.
Yeah, I mean, we are spoiled rotten, when it comes to things like that. They knew it, but they were probably fairly few and far between, but it's just amazing what they did. All right, so here's Euler's method. And it's basically generalizing exactly what we did, but putting it maybe a little more formally. So I'm going to clean the page so you can see it afresh. And just to remind you, to do any of these approximation methods, you got to have an initial value. I mean, otherwise you have nothing to go on. So you have to have an initial value.
And that's going to be your like y prime or y0.
Y0, x0, y0, exactly. Okay. So knowing that, what you have is a differential equation, and they're sort of leaving some of this out, but a differential equation that's usually of the form y prime is equal to some f of x. Let me correct that. Usually some function of x and y. Okay. If I can get my pen back. There we go. Okay. So you have that. And that's basically all you have. Oh, with the initial condition, yeah. Let's see, let's just do it like that. Never mind. Okay. Y0 is equal to, how do they usually write that? Y at x, that's it. Okay. Just getting my zeros crossed up. Okay. Y evaluated at x0 is equal to your y0. So there's your initial point, x0, y0. This thing is your slope, right? It's the first derivative. That's your slope. So at x0, y0, that's your first approximation. Well, then we use the point slope formula that y minus y0 is equal to the slope, which is f, this derivative here, at x0, y0 times x plus, minus x0. Okay, sorry, minus x0. That's basically your point slope formula, right? Yeah, okay. Y minus y0 is m times mx minus, with parentheses in here, x minus x0. Okay. So there is basically what we're going to base everything on, except, one more step, add the y0 to both sides, and that gives you y is equal to y0 plus f of, I can't write, x0, y0 times x minus x0. Okay. Now, this is what they call the linearization as a function of x. Okay? Now, what you do is plug in your x0, y0, which we know is here, and the slope at x0, y0, which you know from your differential equation. So plug that in. And that gives you a...
I've noticed that L of x, that's we've done that in Cal 3 before.
Yeah, you did it when you were talking about differentials, introducing differentials. The linearization is the approximation of where the function's going. That's exactly what this is doing, precisely what it's doing. Yeah, exactly this, okay? You're approximating with the straight line.
Because I remember one time we were doing like area.
Right.
And we had L1, L2, L3, and L4. And we had to, like, I think, do the Lagrange multiplier.
Lagrange, yeah, Lagrange multiplier. That's exactly Cal 3. Yeah. Very good, yeah. Sorry. You've had some pretty good math background. And you have a good mind for it. So use it well. But yeah, Lagrange multipliers, that's the very similar to the technique you use there. They may use the same, the L there is for Lagrange, okay? That doesn't mean linearization.
Yeah,
okay.
No,
yeah, so
Lagrange got that.
they use this. Yeah.
Yeah. I think it's an upside delta or something. It's like,
yeah, that's the gradient.
The gradient?
Gradient, yeah. Okay. Yeah, the upside down delta, exactly. Now, so what you do here is get your, by plugging this in, well, this is your linearization. So what you do next, hey, here's Charles. Okay. We're on Chapter 2, First Order Differential Equations, 2.6, a numerical method, and we're on the bottom of page 77, which is introducing Euler's method, which we're just describing here. And the first step is, go back and review it quickly. Your first order first order differential equation, dy dx is equal to f of xy. Some function here, whatever that is. So that's how it looks. That's a differential equation. Okay? It's a function both of x and y. Okay? Could be. Now, usually it has to be if it's not solvable. If that's just a function of x, you can solve it by separation of variables. No sweat. But this is a function of x and y that you can't solve by separation of variables. You can't solve by the linear methods. You can't solve by exact method. You can't solve by any other methods. But you do know that it's some function there. Weird, difficult, strange function. But it's some function. What does that tell? And you also have the initial condition that at x0, your value for y is y0. That's your basis for beginning. So what you do, you evaluate this slope, because this is your just your first derivative, is your slope at that point. Okay? So you evaluate that. This is x0. That's a pretty ugly 0 there. Okay. Evaluate the slope at that point, and then you have a point and a slope. There's your point. Here's the slope. So your linearization, your first guess here, is that y minus y0 is equal to the slope times x minus x0. It's point slope formula. And then add the y0 to both sides, and you have y is equal to this. So what you do then is, this is a linear approximation to what that function's doing. Now here's the picture illustrating what we're talking about. Here's this unknown solution curve. You just know it has a point here. You also know the slope is there because that is your f of x0, y0. So you basically are using that line that you do know a value for, and then go a little bit further in x. Now they went a lot further. They went over here to x1. Now they're missing it pretty badly, but still they're in the ballpark. If they had just gone a smaller delta x, like maybe just to there, made the x1 there, then they'd have been really close. Okay? That would have given them a new value to do. So take that new value, x1 we'll call it, and plug that in here. Okay? And see what you get when you get your y1 here. Okay? So now you have a new point, x1, y1. Okay, what you do with that, plug it back in there, get you a new slope at that point, which is going to be pretty close to the actual thing, but not exactly. And then do the same thing again. The y2 is then going to be y1 plus alpha of x1, y1 times x minus x1. Okay? And then pick another, go that little increment further from x, and make that your x2. And then do it again for y2, then plug it back in there and do it again. And this is the procedure that you do. This is called Euler's method. Okay? So, like I was saying, I just said it, let me write it. Once you have this, then pick another value for x, not far from the original x. Your x0 was here, move it up a little bit. In our first example, the x0 was 2. We're trying to estimate the value at 2.5. So they went 2.1. And they're going to do about 0.1 until they get to 2.5. So your L of x1 is going to be, that's going to be y1, okay? And that's going to be y0 plus f of, because this is all you've got to go on here, x0, y0 times x1 minus x0, okay? Plug in your x1, that little increment further, 2.1 or whatever it happens to be, here, come up with a new y1. Then you take that y1 and plug it in here. y1 prime is equal to f of x1, y1. Get the new slope at that next point up there, okay? And then use that slope back here and this again. You feed that in here. You feed the y1 in here. You feed the x1 in here. And you have your formula over again, okay? Over and over again. So your y1 is equal to, now, here's what they're calling that little increment. x1 is equal to x0 plus h, okay? Now, if you do that at this step here, this makes it a little easier, okay? Then this y1 will be y0 plus f of x0, y0 times Now your x1, where I put x1, put it x0 plus h. Whoops, oops, oops, don't close the parentheses too soon. Okay, minus, guess what? x0. Okay, well, guess what? The x0 minus x0 goes away. So now we have that your y1 is equal to y0 plus f of x0, y0 times h, because that's all you got left here. Okay? Now, that's helpful because now you don't have to do your new value every time, but that gives you a y1, and your x1 is just x0 plus h, and then what you do is, and the h is fixed. You decided 0.1, 0.05, whatever it was, that's fixed. So then your y2 will be y1 plus h times f of x1, y1. Now remember that what f is? That is your slope. Okay? So this is what you do every time. You don't have to go back and reinvent the wheel. You just do this formula over and over again. And this is Euler's method. What the h is called is the step size. H is the step size. Okay? The smaller the h, the closer you're going to hang to that curve. And every time you hang close to it, then the next one's going to be closer. Too long, like this one they showed here, if you let that be your h, the difference between x0 and x1, then you're off pretty far. That's pretty bad. What if you had chosen an h down here, okay? If you had chosen the h down here, you'd have been right really, really close. Then you evaluate it again, you're closer and you're closer, so you come out much closer. However, it takes you a lot more steps to get where you wanted to go. What if where you wanted to go was up here somewhere? This one you could do in 2 steps. This one, if you chose that, you may take 10 steps. And of course, that's doing a lot, but you'll get a lot closer that way. If you go from this one and then evaluate the function here, you're evaluating the slope from this point, but you're moving from that point because that's your x1, y1. So you wind up getting off a little bit. The smaller the step size, the closer you are. Okay? So basically, this is called a recursive, a recursive formula. And here's what it is. I want to make sure I got my index the same thing. Y of n plus 1 is equal to y sub n plus h of times f of x sub n, y sub n. Okay. That's your recursive relationship, and you just step as you go. Okay. And let n go 1, 2, n is just a counter, 1, 2, 3, 4, 5. So that's Euler's method. All right, let's put it to practice. Okay, and fortunately we're going to put it to practice in the very problem we were working on before. So here's your initial, this is your initial value problem. Y prime is equal to 0.1 times the square root of y plus 0.4 x squared.
Is this the last problem?
What's that?
Isn't this the last problem we just did?
Yeah, that's what I'm saying. This is the same problem we were working on before. Okay? With the same initial condition, y of 2 is equal to 4. That's your initial value. Okay? It says use Euler's method to obtain an approximation for y of 2.5, and it says first use h of 0.1, and then we'll use h of 0.5. So we'll do h equals 0.1, and then later we'll do, and our target is to get y of 2.5, at least an approximation for that, and then we'll do a h of 0.05, and see how much better we get. Okay? Now, and again, this is not an equation you can do separation of variables. It's not an equation you can do linear method because the square root of y wipes that out. It's not one you could do exact method. It's not one that's homogeneous. There's just nothing, none of the techniques we know so far can solve that. So we're going to rely on a numerical approach and get an estimation. Okay? So, first thing we do, this is our x0, this is our y0, and this is our alpha of xy. Okay? So, Euler's method is y1 is equal to alpha of x0, y0 times, whoops. Let me go back and get it correctly. Sorry. I want to do it the same way the book did. I sometimes like to put the y at the end. y0 plus alpha of x0, y0 times x minus x0. Okay? Except here we're going to put x1. Okay? Right. Now, I think they write it that way, don't they? Oh, I'm sorry. I'm doing the long way. Let's go back and I could have put it in there. The short way, the x minus x0 just came out h. So this is h times f. Goodness, I can't write. Okay. H times f of x0, y0. Okay. So there's no x1 listed here yet. We'll get that on the next step. All we have are things we know here. We pick the h, we know the x0, you know the y0, and we can plug in the x0, y0 and get that. Okay. Now we've already done the first part. I don't know if you weren't here to do it, so let's do alpha of x0, y0. And in this case, it's 0.1. Now, I really sort of bugs me here. The problem has this 0.1 in it, and our h is 0.1. That's just happenstance, okay? Most of the time, they're not going to be the same. So don't get them confused. The square root of 4, because that's your initial value, y0, okay, plus 0.4 times, and your x is 2 squared. So this was 0.1 times 2 plus 0.4 times 4, and this was 0.2 plus 1.6 equal 1.8. So that's your alpha of x0, y0. Okay? So your y1 is equal to, y1 is equal to y0, 4 plus 0.1, that's the h, times this thing here, 1.8. And just like before, this gives us 4 plus 0.18 is 4.18. It's exactly what we got before. You were in here before. In fact, I'm not sure you came in right about the time I'd already gotten that. Okay. Yeah. Okay. So that was on the board before. Now that's what we use for, this is now our y1. Our x1, by the way, because we went up by 1, is now 2.1 because we went up by 1h. So now our y2 is going to be y1. Let me write down the formula here. Y sub n plus 1 is equal to y sub n plus h times elf. I don't need that parentheses in front. Second time I've done that. H times elf of x sub n, y sub n. Okay. So our y2 is going to be y1, 4.18, that you already have in your calculator, plus 0.1, that's the same. But now we evaluate this function by plugging in x1, y1. So this will be 0.1 times the square root of 4.18. This I had on the board, I think, when you came in. Okay. Yeah, plus 0.4 times 2.1 squared. You did it, I think, right when you came in.
Oh yeah, that whole thing right there. That was 1.96.
So yeah, okay, that was, this part was 1.96. So do 1.96, you already figured it out, 1.96 times 0.1 would be 0.196. So our y2 is going to be 4.18 plus 0.196.
Yes, sir.
That's 4.376. Something pretty close to that. Yeah, they have one more digit here. They do
4.376.
Yeah, in the book they do one more digit and do 6.8. Okay, and that's now our y2. Okay, y3 is going to be this number here, 4.3768, that's our y2, plus your 0.1, that's your h, okay, times what's your x0, y0, which is 0.1 times the square root of your 4.3768, goodness, that's ugly writing, okay, plus 0.4 times your x2 is your 2.2 squared. Okay? And basically, see, this can be programmed on the computer fairly simply. You just make that a function and then plug in the values. The x you can just do stepping up by 0.1. The y you calculate each time, then you plug that back in and you just go through town. That is such an ugly 7. I've got to do something about that. Okay, that is one of the ugliest 7s I've ever seen in my life. Okay.
Yeah, you could definitely write that on like MATLAB or something.
What's that?
You could definitely write that formula, the yn plus 1.
Yeah.
Plus the h of x.
Yeah. Yeah, and you love that. I remember. Yeah. Okay. But yeah, it's all. I mean, you could do it in a simple basic form. Well, I don't think they use basic anymore. Any computer language you can set this up to do and to calculate, and you just feed back in over and over, and they do this. You see, this gets you to 2. This one uses 2.2. The next one's going to be 2.3, and the next one will be 2.4, and then when you use the last one, 2.5, that will give you your last y. And they get, and I'm not going to make you do that, but when they get up to 2.5, x of 2.50, why they put the 0 there, I'm not sure. They got to, I know why, but 5.0768. Okay. Now, that's doing 0.1, okay? I don't have room to do it on the screen, but you know what happens if you're using 0.05. Then this changes to 0.05 every time. The h changes, and that makes your calculations. You have to do twice as many to get from 2 to 2.5 because you're going up half the step size. This one took 5 steps. because you went up 0.1 each time. Next, you're going to need at least 10 steps to get up to that. But when you do, using 0.05, you get 2.50 being 5.009. No, 5.0997. Okay? Now, I don't know if anyone knows the exact value, because this isn't solvable with the exact value, but there are better techniques to do, and my guess it's not going to be too far from 5.1. Okay? Maybe a little bit, but
Did you need me to solve Y3?
if you wanted to, you certainly can. Did you do it? Is what?
4.59.
4.59. Give me a couple more digits.
4.913659.
Okay. 4.59 what?
4.59136.
14 then. Okay, in the book they gave 4.5914, right on the money. That would be at 2.3. Okay, because that's what you went up by one step for 2.2, that gave you 2.3. You do the same process again, but this time you put this in here, put it in there, and then use the 2.3 there. Now,
So why are we increasing it by 0.1?
they just told us to. They said, yeah, they use the H of 0.1.
Oh, okay, and then H is 0. Okay.
Yeah. The next time you do H of 0.05. So it's going to take you 10 steps. You see, that takes 5 steps to get from 2 to 2.5. See, that's what we're gunning for. Y of 2.5. Okay? It took you 5 steps to get there, and you got this answer. Using H of 0.05, it's going to take you 10 steps, because you're only doing half as far each time. But you come out with a better approximation. Now, why I say better approximation is you go back and look again. This is the one they're talking about, I think. Yeah. This isn't the same curve as this one. This one right here. And you see your slope, because it's curving up, it's concave up, your tangent line is always going to be beneath that. So you're underestimating a little bit. And every time you're underestimating a little bit. When you do a smaller one, you're still underestimating a little bit, but it's a littler bit, so that's getting closer. And that's why I said my guess is the answer is closer to 5.1 or maybe even greater than 5.1. But who knows what the exact answer is, because this one's not solvable by any analytical means. There are better approximation techniques, and perhaps we're not going to get to it, but we're going to talk about it pretty soon now. So what we've just done, we didn't do all those. If you want to do them all, knock yourself out. But they have a table in the book of the 5 steps that got you from 2.4 to 2.5, 5.0768. Then they did, with 0.05, 10 steps that got you from 2.4 to 2.5 times 2.5 comma 5.0997. The one I put here. I just put the last one there. Okay. Now, do you need to see the 0.05? I mean, I'll be glad to do it, but it's just more of the same. It's just a different increment here, and you do more steps. Okay. Thank you.
But theoretically, on that 0.5, though, we would get to Y10, right? Y sub 10.
You get to 2.5 in 10 steps. Yeah.
Yeah, so I'm saying like the Y sub values you got, like you have Y sub 1, Y sub 2, Y sub 3.
Right.
That's your steps.
Yeah. Yeah. Well, those are just the number of steps. Yeah. The step size is 0.1 or 0.05. It just takes, if I'm going from here to there and I take these kinds of steps, it takes me 5 steps to get there.
Yeah.
If I take these steps, it takes me 10 steps to get there. Okay, that's what it means. You're just doing smaller increments, but you're getting closer, you're staying closer to the real curve. Okay. Now, example 2 here, okay, forgot to get up my watch. Okay, yeah, okay. Okay. Example 2 here compares the approximate and the actual values. Okay? They're going to choose one that we can do. Okay? Here's an initial value problem. Y prime is equal to, we've seen this one before too, 0.2 times xy. Okay? With an initial condition of y of 1 is equal to 1. Okay? It says use Euler's method to obtain an approximation of y of 1.5 using first 0.1 and then h of 0.05. So we're trying to go to y at 1.5, and we're going to use first h of 0.1, and then we're going to use h of 0.05. Okay. Now, the reason we're doing this one is we know how to do that. We don't have to use Euler's method. We can solve that analytically very easily. Separation of variables is a piece of cake. And we've done it before, okay? So we don't have to redo it. But let's do it. So this is our f of xy is this thing. That's their slope, okay? The y prime, f of xy. I really wish they wouldn't call it f of xy, because then I want to take a derivative of it to get the slope, and it's not. That is a derivative. I wish they'd just leave it as dy dx, okay? And leave it at that. But they like to call it that, okay? And your Euler's method would be y to n plus 1 is equal to y of n plus h f, and this is why they call it f, of n, x sub n, y sub n. Okay. Now, got to get started. So your first step would be y1 would equal y0, and by the way, here is your y0, here's your x0, here's your h that we're going to do the 0.1, and your f of, this is your f of x right there. So this will be, your y0 is 1 plus 0.1, we're going to use the first h, times, and let's just go on and plug in what it is, 0.2 times 1 times 1. That's going to be really hard to do, right? Okay? So what we have here is your y1 is 1 plus 0.02, right? .02. That's the first one exactly. Okay. Got it?
Yes, sir.
All right. So y2 is going to be 1.02 plus 0.1 times. Now we have to evaluate this. Goodness, my nose is itching like crazy. We need to evaluate this, and this will be 0.2, that's what was given here, times your x is 1.1, because you stepped up 1, and your new y was 1.02. So there's calculator time. 1.02 plus 0.1 times 0.2, which is 0.02, times 1.1 times 1.02. 0.042?
Yeah, is that correct?
0424 is what they got.
Yeah, 4244.
424. They rounded there, okay? If I were doing this on my calculator, I'd leave that whole string of thing in there, put that and store it, store it in memory, and then when I want it, I recall it. So your y sub 3 is going to be that thing there, 1.0424 plus, now since that's always the same, let me go on and just do 0.02. 0.1 times 0.02 is 0.02 times your new x is 1.2 and your new y is 1.0424. Okay? It's pretty easy to calculate, right? So leave that other one in there and just add that thing to it.
Oh wait, you multiplied the 0.1 and 0.2.
Yeah, I multiply those two together. They're always the same, so keep you from having to push the button so many times and hurt your thumb. So I wanted to save your thumbs.
1.067.
0.067. Need one more digit. 5?
6745.
4, 5. Okay, so we're around there. So there's your y3. The y4 is going to be that number. So just whatever you had there, leave that in there. 1.0675 plus 0.02 times, this times 1.3. We stepped up by 1, and this will be 1.0675. These are just easier calculations. So 1.095 what? 2? Yeah. See how the book, yeah, perfect, perfect. And then your y sub 5, which should be getting awfully close. This is the 1.0952, whatever you had in the calculator, leave it there, plus 0.02 times 1.4 times 1.0952. Nine. Okay. That's what they have in the book. Okay.
1.1259.
Yeah. Okay. All right. So we've got that. I'm going to write it up here. Y of 1.5 is approximately 1.1259. Okay. Now. All right, to erase most of this?
Yes, sir.
Okay. I really almost wish I could keep some of it there, but I'm not. Now the book and the table in the book, they do your errors as they go, okay? And I'll point that out later, but I'm just going to do error at the end, okay? And we're not going to do all these, I promise, but we'll do a few of them and see how close we get, okay? So now our y1, when we're using h of 0.05, okay, just to get the changes, that's going to be y0, which was 1, plus 0.05 times 0.2, that was from the problem, times 1, that's your x0 times y0, which is 1. Okay, so the only thing that's changed now is that step size, and I think I can do this one almost in my head. This will be 1.0100. I believe that's right. Yeah. That's your y1, right?
Yeah.
Yeah. Okay. Now, using that, 1.01, I'm going to write all those extra zeros down. Plus, now I'm going to combine these two together. This is 0.1, 0.05 times 0.2 is 0.1, right? Times my new x is 1.05. 0.01. Yeah, oh yeah, I knew that. 0.01. Let me write that better. Okay, and the new y was 1.01. Okay, that one should be pretty easy to calculate.
.02.
0206.
Yes, sir.
Okay.
1.020605.
Yeah. Okay, that's good enough. Okay, the y3 was going to be 1.0206 plus 0.01 times 1.1 this time because you step up by 0.05 times 1.0206. So whatever you had in the calculator, just add to it 0.01 times 1.1 times
1.03183.
03183. Is that what you said?
Yes, sir.
Okay, let's see what the book got. Yeah, they rounded. All right, here we go. Justin, right?
Yes.
Okay. And since we do have a couple more people here, let me say what I said earlier. We're getting well into July now. We're still early, and I've gotten 2 papers in so far. And remember, the paper is due last day of class, which will be also in July. I don't remember what day it'll be, but it'll be, let's see, whatever. Today's the 9th. Plus 14, plus 20, no, plus 21 will be the 30th. I think that may be the last day of class. Huh?
We're at the door almost.
Yeah, I mean, we just got not much.
I guess this class is so intense in here. Yeah, I didn't really take time to really think about it.
All right. We're doing what they call Euler's method for approximating differential equations. Now, it happens to be this one we don't have to approximate. We know we're going to go back and calculate what the exact value is. We've done it using a step size of 0.1, and that gave us 1.1259. Okay? We're stepping through using 0.05 this time rather than 0.1, and we're seeing that we get smaller changes. Okay? So we're going to use the previous one. And here's Euler's method. Y n plus 1 is going to be y sub n plus h, which is your step size, times f of x sub n, y sub n, the previous one. So this will be, the previous y was 1.0318, exactly what you calculated just now, plus, and I just multiplied the first two together. 0.05 times 0.2 is 0.01. Times, now the step is 1.15 times the previous one, which is 1.0318. Okay?
1.04369.
04369, so I'm going to put 7. And that's what the book got. So then the next step, y sub 5, will be 1.0437 plus that 0.01, that's the step size times that first multiple there. That doesn't change. So, and this will be 1.2 times 1.0437.
1.056222.
Okay, 562. And that's what the book got. Now, that was with the x sub n. Let's do just one more. Y sub 6 is equal to 1.0562 plus 0.01 times 1.25 times 1.0562.
1.06942.
Okay. And they got that. Okay, now the reason I stopped there, this value here, y sub 6, what I've been calling y sub 6, yeah, that is corresponding to x of 1.3. So your x was 1.30, okay? Here, you stepped up one. So this is your, I can't write. My pen is sliding. Okay. The x sub 6 is 1.30, okay? For your y sub 6 being that. Now the only reason I did that is to compare it to 1.3 that we had before when we did the h equal 0.1. I probably should have done different colors. That would have made sense, but it's too late now. When x was 1.3 before, your y was 1.0675. So you see you're a little bit greater here. And my guess is you're more accurate, okay? Now, I don't have room and we probably don't have time, but you see it's a pretty simple process to just keep on going until you get to y sub 10, which is going to be at 2.5. So I'm just going to copy from the book, and my y at 1.5 using 0.05 is going to be 1.1259. Wait. 95, okay. It can't be the same. It just switched the digits on me, and I was dyslexic. Huh?
I do have a question.
Okay.
So if the y1 and the y2s, the number keeps changing, could you just basically, I guess, divide like y2 by y1, that value, and see what it's like multiplying by? And then theoretically, instead of like doing all that, just
Okay. If this was linear, that would give it to you exactly. But if it was linear, we'd know the answer.
like I've been dividing some of them, and it's like I'll divide like 1.562 by 1.04369.
Right.
And I get 1.012, and then I divided the 1.0318 by 1.02, and I got 1.011.
Yeah.
So I guess that's what it's multiplying by.
Yeah, but you see, it changes every time.
Because of the h value.
Yeah.
I think it's the h value.
Yeah. But you see, if that was exactly the same ratio, yeah, that would be the easy way to do it. But they're not the same ratio. One was 1 point, whatever you just said.
Yeah.
And the other was a little bit different, and the other was a little bit different. So this is probably a little more precise than that. But you see, it's not a lot of difference there. Let's go and actually solve the differential equation. Okay? We can do that. This is dy dx is equal to 0.2 xy, right? Solved by separation of variables, right? This is dy is equal to 0.2 xy dx, and then divide both sides by y. Okay? And then we integrate both sides. Okay? And this will be log y is equal to 0.2 x squared over 2, right? Okay, plus C. Okay, well, let's clean that up a little bit. Log y is equal to 0.1 x squared plus c, and then exponentiate both, and you get y is equal to, I'm going to change my c, by the way, okay, and that'll be c e to the 0.1 x squared, which we've gotten before, okay? Now, what we're going to do now, I don't have much room, so I'm going to erase what I just did, okay, and plug in our initial value, 1, 1. So 1 is equal to c e to the 0.1, right? If I'm plugging in my initial value, y is equal to 1 is equal to c times e to the 0.1.
Yeah.
Okay? And so c is equal to 1 over e to the 0.1. Yeah, solve it. Or e to the point minus 0.1. That would do it. Well, you just bring it upstairs. E to the minus 0.1. Should be the same answer.
0.904.
0.904?
Yes, sir.
Okay. Let's see if the book got that. Well, I don't care if they got it or not. Okay. So, I'm going to plug back in again. Y is equal to 0.904 e to the 0.1 x squared. Okay? Now, let's see what we get. 0.904 e to the 0.1 times 1.5 squared, which is 2.25. Wait a minute. They get a different answer. Hold on just a second. They got 0.1, not 0.9. No, they got 1. Where do we mess up?
Maybe we go back, I mean, does it go back to when we tried it 0.2 divided by 2?
Okay, wait. Let me. They got c is equal to 1. The true or actual value are calculated from a known solution of that. Now, why is that the case? Did they round it? Okay, let's do what you said. Let's go back here, and I think this is what you said. Put log of 1, which is 0, is equal to 0.2. Well, make that 0.1 x squared plus c.
Well, actually, what if we go back? Because I'm looking at the 0.2 divided by 2. You get 0.1. That is correct. We have 1 equals c e to the 0.1. we go ahead and just solve for e to the 0.1 right there instead of putting it c equals 1 over that?
Okay. Yeah, I think that's what I was doing here. Okay. Let's erase some because we got too much on the board here. We've agreed that this gave us that, I think. Right? Now you want to solve for C at this stage? Is that what you're saying?
Well, I mean, you still get the same 904, so I have no idea.
Say again? Okay.
You still get the 904 from the way I was thinking about.
You got it. Okay. Let's do it this way. Log y is equal to 0.1 x squared plus c. Right? If you plug in 1, 1 here, you get 0 is equal to 0.1 plus c. So c was equal to negative 0.1. Okay? And so if you put that in here, minus 0.1, and then exponentiate both sides, you would get y is equal to e to the 0.1 x squared minus 0.1, which would be, I think you get the same thing. E to the negative 0.1 is 0.904. Isn't that what you got?
No, actually, e to the 0.1
is the negative 0.1.
Is to the negative 0.1 is 0.904.
Okay.
The positive is 1.105.
Okay. And then reciprocate that.
What do you mean by that?
Just 1 over x. 1 over.
Oh, 1 over x on the.
Yeah, because you see, you have 1 over e to the 0.1. You see, what they did, they rounded, which is okay, but it's not really very precise. They rounded that to 1.
Yeah, 0.904.
Yeah. Sorry. Okay. No, they didn't. Okay. They left it as, I'm sorry, I misread their answer. And I think we'll get the same thing they did. Okay. We got the same thing. They didn't round the way we did. Here's how they wrote their answer. And it is the same answer, by the way. Where do I write this? Okay. I'm sorry, I misread their answer. I thought they had come up with C. How they wrote their answer is y is equal to e to the 0.1, and then they did x squared minus 1, which is the same thing, basically, we did. They just substituted. See, this is e to the 0.1 x squared times e to the minus 0.1. You see, that is the same answer. It's just a little bit neater form. Okay, so we got the same answer. They just did a different C than what we did. So let's use theirs because it is a little cleaner. Okay, a little bit, not much. Okay, so let's use this formula. And we'll get y is equal to e to the 0.1 times 1.5 squared minus 1. We should get the same answer we did if we had carried it out. See what you get there. That's 2.25 minus 1 is 1.25 times 0.1 is 0.125. So e to the 0.125.
1.25
1.133.
Yes, sir.
One more digit.
1.
1. Yeah. That's what they got in the book. Same thing we would have gotten if we used a .094. Okay? Except ours was rounded, theirs is not. Okay. So, using an H of 0.5, they came 1.1259. Using 0.05, we got 1.1295. Like I said, it was closer to 1.3. Okay, 1.13. The exact answer is 1.1331. So you see, by reducing, and then they go into absolute error and relative error. Okay? And I don't know why they go into that here, but they do. The absolute error is the difference between them. The difference between the actual and that. So the absolute error is the absolute value of the difference between 1.1331 and 1.1259. And since I put the biggest in front, and that's an error of not very much, 0.0072 or something like that, 73. Absolute error 0.0073. Whereas for this answer, this is 0.1 step size. The absolute error, I'm just going AE of 0.05 would be 1.1331 minus 1.1295. Okay. Goodness. Let me clear some space here. I can't read my own writing here. Okay. We're not using that one anymore. Okay. Why won't that erase? Okay. The difference there is 0.00. .36. Okay. They got 3.7. I don't know how, but they got 3.7. Whatever. Okay. Now, if you there's some round-off error involved with it. The absolute, that's the absolute error. The relative error is the absolute error, 0.0073 divided by the actual amount, 1.1331. Do that on the calculator. I can't do that one in my head. And they got, I think, about 4 zeros and a 6-4. Is that what you got? 0.0073 divided by 1.1331. The absolute error divided by the actual amount.
0.6821.
Say that again.
0.6821.
0.6621?
0.6821.
Wait. 0.0073 divided by 1.331.
How many zeros between those?
You're going to have 4 zeros, I think, as your answer, and then some numbers. What you get?
0.00833.
Okay, they got 6.4. Now, I don't know how they actually got that.
Oh, you know what? I see where I messed up.
Okay.
My thing did 0. Alright, so it's 0.773.
Okay. I don't think so. 0.0073 divided by 1.331. No differential equations, we'd be
Okay. 0.00644.
0.0644, right? Okay.
What happened? My thing like duplicated and it had 0.073 divided by 0.007.
Oh, okay. So what you do, move it 2 places, and that gives you a 0.64% error. Okay. On the other one, do 0.0037. That's what the book used, divided by 1.1331. Say again?
0.0027779.
They got 32.
Oh, I got it.
319, so 32. So this will be about a 0.32% error. So you see, you cut your percent error in half by having the step size. So yeah, you're going to get better and better. But the trouble is, the odds are when you have it again to 0.025, then you're probably still going to have a percent error of 0.0016. So so you see, you're having to do a lot more steps to just get an incremental amount of precision increase. So at some point you say that's enough. Well, the problem here is that the Euler method, what error you get, you propagate it, okay? There is another one, and here, they have it here as a caveat. Euler's method is just one of many different ways in which a solution to differential equation can be approximated. Although attractive for its simplicities, it's seldom used in serious calculations. So why did they spend this much time doing it? Just to give you an idea, okay? It was introduced here simply to give you a first taste of numerical methods. We'll go into greater detail in discussing numerical methods that have significantly greater accuracy, notably the fourth order Runge cut-up method, referred to as RK4. That'll be in chapter 9. I don't think we're going to get there, but there are much, much better ways to do it. And then there's numerical solvers. Basically use, I'm guessing, either finite difference or finite something. There's a couple of different models you can use, and these give you numerical solution curves. That's what I'm guessing they used in the book to get their curve on that previous example. But here's the one we just did, I think. The exact solution is the blue curve here. The Euler's method, you see, we were off some, okay? But this is going, well, this is a different, no, it must be the same one, okay? But they started at 0, 1 here. So Euler's method did that. The RK4 method comes closer to exact, but it's still an approximation in between the various values. It actually calculates exactly on the digits there, 1, 2, 3, and 4, 0, 1, 2, 3, and 4, and approximates in between. Okay? Now, here's a problem with numerical solvers, though. If you happen to have a really bizarre equation, you might get something that looks like this, and that, they say, is not very helpful at all. So you have to be very careful with your numerical solvers that you pick the right space size and everything else to get it to work. That then finishes 2.6. If you can, do, I think it's in the back of the book, do example 1. If it's in the back, 3 if it's in the back, any of the odds 5 through 9 if they're in the back, 11 if it's in the back. So there's not too many here to do. If you need more practice, the Chapter 2 review questions, the odd numbers of those are in the back. This covers the entire chapter. 1, 3, 5, 7, all the odds are in the back. So any of the odds 1 through 11 should do fine. Any number 13 should do fine. 15 should do. 17, any of the odds, oh wow, 19 to 25, 27 to 31, no, 27 to 29, 27 or 29, 31, 33 or, no, 33, 35, 37, 39. So any of the odds that are in the back of the book, if you need more practice, do those. Now, I know we don't have a lot of, well, no, we have more than half an hour left. Since we did finish this, let's take a quick break here. Now, we're not going to do Chapter 3, because nothing in our course description said anything about modeling. Now, some of you might be good models, I'm not, but so we're going to skip the modeling part. I can't do runways, okay. So we're going on to Chapter 4. Okay, and that's where we're going to pick up when we get back. Well, let's take a quick break, and why I'm wanting to take a break now is so I can get your second test run off for you. Okay, and that way, when you come back from break, I should have that.
So next week we would start.
Sorry, that was probably longer than a 5-minute break, but it took a while for me to make the copies. We are recording again. Let me go over test 2. Remember, I need to show work. I need for you to show work, okay? The first one, I think, is going to be pretty easy, and there's not, I mean, don't make more out of it than what it is, but you won't have a lot of work to show there, but just give a little bit of rationale why you fill in those 2 answers, okay? Number 2, just show a little bit there of why you got the answer, okay? And then number 3, the autonomous linear first order differential equation, single credit. Yeah, that's all from that either first or second section in Chapter 2. And again, there's not going to be a lot of stuff you need to show, but just how you got to get your answer. Okay. Now, number 4 is basically just asking you to classify the differential equation as either separable, exact, linear, homogeneous, or Bernoulli. 5 choices there. And I put a number of blanks after each one, trying to indicate that some may have more than one. And sometimes I just didn't have room to put more blanks. But anyway, you get the general idea there. Now, how do you show your work on that? Well, here's what. If it's separable, show it how you separate the variables. If it's exact, show how you determine that. Remember the test for exactness? Anybody?
Is that the
M and N?
M and N?
Yeah, right. Okay, you write it as in differential form, and the function that goes in front of the dx is your m, the one that goes in front of the dy is the n, and you take the partial of m with respect to y, not x, and take the partial of the n with respect to x, not y. Show that that's how you determine that.
Now, do we take the interval, or I forget?
No, you don't have to solve the problem. You just show why it's exact. Linear, remember it had to be of the form dy dx is equal to, plus p of x, y is equal to f of x. So get it to that form and show, yeah, this is linear. See, these are not all set up this way. You're going to have to do some work on them to get them to do, okay? If it's homogeneous, what does it mean to be homogeneous or homogeneous? Well, that means that you have the same, when you write it in differential form, all the terms for both of your d's are got to be the same degree, right? So that's what you just need to show. So you see, for an exact and a homogeneous, you have to write it in differential form. Okay? Bernoulli, I think you also have to write it in differential form. No. Let's see. Bernoulli was, no, you write it in, it's a form like on page 73, if you got a book, on page 73, equation for it. Looks a lot like a linear form. dy dx plus p of x y is equal to f of x, but then you've got a y to the n in it. So get it into that form and say, therefore it's Bernoulli's. Okay? So basically that's the thing. Some equations may be more than one kind. Do not solve. Don't go about solving these, but just show why it's whatever form you say it is. So manipulate what you got here until you get it into separable, separate the variables. Exact, write it in the differential form and show that the m of x, the partial of m of x with respect to y is equal to the partial of n of x with respect to x. Okay? It's m of xy with respect to y, partial of n of xy with respect to x. Okay? Linear, write it in the linear form. dy dx plus p of xy is equal to f of x. Write it in that form, say, therefore it's linear. Okay? And then the homogeneous, write it in differential form and show that every term in both things has the same degree. That's all you have to do for that one. Bernoulli, write it in just like you did linear. dy dx is equal to p of xy, plus p of xy is equal to some f of x or g of x, whatever you want to call it, times y to the n. That makes it a Bernoulli form. So just show why you classified it each way. Okay? That's number 4, and that's the bulk of the test right there. Okay? Bunches and bunches of those. And then in problems 5 and 6, you actually solve the given differential equation. Okay? And so do it whatever method you want to try to find to do it. That's 5 and 6. Then number 7 is solve an initial value problem. Whichever form seems like is the best to do that. Okay? Then an implicit solution for the differential equation. And that was, I can't remember which section that was. You'll find it. I just can't lay my eyes on it right now, but when we did that, the implicit solution, okay, and then number 9 is the Euler's method, what we just did. So, and that obviously is going to take showing some work on that one. So
number 9 would be 2.6.
Yeah, number 9 is 2.6 for sure. I wish I could remember which section 8 was. I don't remember it right off the top. Okay, so let me get this back, my stack in order, otherwise I never can find anything. Whoops. There we go. All right, so for people at home, I guess you realize I just passed out test 2. Come by and pick them up whenever you can, okay, or get in touch with me some way. What we're going to do now, I think I just hit the button twice. I think I was. Okay. I went to erase the screen and hit the stop button again. So.
Well, your time's at like 1 hour and 44 minutes.
Okay, we only got, what, about 15, 20 minutes left? Okay. All right, let's get done what we can. Example, chapter 4. We're now going to higher order differential equations. Chapter 2 was all first order differential equations. Okay? So here we move to a higher order. Okay? Now I'm not a big fan of their preliminary theory linear equations. Okay? Every chapter starts with a bunch of stuff at the beginning that you go through and through and through, and then finally you get to some real life problems. Okay? So this one is not too much of that on the preliminary theory, but let's get what it is. All right? And a lot of this is just terminology. Okay? In Chapter 2, we were able to solve a few first-order differential equations by recognizing them as separable, linear, exact, having homogeneous coefficients, and then, a few others, Bernoulli and other things like that. Even though the solutions were obtained in the form of a one-parameter family, why one-parameter family? First-order differential equation, one-order family. Now, this family, with one exception, they said, did not represent the general solution of a differential equation. The general solution is a family of solutions defined on some interval I that contains all solutions of the differential equation that are defined on I. Only in the case of linear first-order differential equations were we able to obtain general solutions. Okay? So basically we're starting off with, what do we mean by general solution? And again, this is mostly verbiage. Okay? What it is a family of solutions, okay, defined on some interval I, okay, that contains all the solutions. To that differential equation on that interval. Okay. Now, I don't know if you realize, because it wasn't really obvious, that we weren't finding always the general solution. We'd find solutions, but quite often we'd say a solution or an solution, or something like that. Some solutions, we're going to get into this a little bit more. Okay? Now, just hang on to that concept for a while. We're coming back to it. Okay. Now, let's look at another issue. Initial value problems and boundary value problems. Okay? In section 1.2, we define initial value problem for a general nth order differential equation. Not just first order, but nth order. For a linear differential equations, and not all the ones we're going to be doing, but most of them are. The nth order initial value problem is, so here's how you set up your thing. Here's the differential equation. A sub n of x. Now that's just a coefficient function of x, okay? And this n there is just a marker, meaning it goes with the nth derivative, and this is y, nth derivative of y with respect to x n times, plus a sub n minus 1 of x. That's the coefficient function that goes with the dn minus 1, y dx to the n minus 1. These n minus first derivative. And you mark your way on down until you get to the a sub 1, and that's some function of x, dy, the first derivative with respect to x, plus a sub 0 of x times y, and this is equal to some g of x.
Question.
Yes?
It's going towards kind of run through a geometric series from Cal 2.
it's written a lot like that, okay?
Like chapter, I think that was chapter 11, maybe, or chapter 10. Or like,
Okay, I don't know exactly which book you used, but that sounds about right. That's usually where those showed up. These A's are not in any way related to each other. My guess is those A's were, okay? These A's are just the coefficient function. But this could be a 1. This could be a 0, okay? This could be a 7/3 pi r squared times the log of n to the second power, log of x to the second power. It's just some function of x, okay? It may be not even have an x in it. It may have just a number in it. It may have 0 as the number, but it's some function of x. The key is there's no y's in any of these coefficient functions, only x's. Because for this to be a linear differential equation, this can only have one power of this with no other y's or any other derivatives in this term. This can only have that one to the first power and no other derivatives of y or y showing up here all the way down. That's what makes it a linear nth order differential equation. Now, if you have that, if you have nth order differential equation and all your coefficients don't have any y's in them or any derivatives of y in them, they're only functions of x, then for your initial values, you're going to need to have a y at x0 to be y0. You also need to have a y prime at x0, same place, and that's going to be y1, okay? They call this one y0, call that one y1. You're also going to have a y double prime at x0, same value of x, x0, and that's going to be called your y2. And then you've got to have your y triple prime, okay, also at x0, and that's going to be called y3. And you're going to have these going all the way down to y to the n, goodness gracious, okay, n minus first derivative of y at x0, and that's going to be called y to the n minus 1. No, yeah, y to the n minus 1. Okay, you're going to need an initial value for every order that you have of your derivative except the last one. Now that counts a y0, which is the 0th order derivative, first order derivative, starting from here, here, the 0th order derivative, first order derivative, second order derivative, third order derivative, up to the n minus first derivative. You're going to need an initial condition for that. You just don't have one for the last one. Okay? So, this is an nth order differential equation, and you have the 0, 1, 2, 3 up to n minus 1. That's exactly in initial values. If this is a 7th order differential equation, you've got to have 7 initial values. Y at y0, y prime at y0, up to y, the 6th derivative of y at x0. Saying y0. Okay. That's required for your initial value problems. Okay. Now, in section 1.2, way back then, we stated a theorem that gave the conditions under which existence and uniqueness of a first order initial value problem was guaranteed. That theorem, the theorem that follows here, gives sufficient conditions for the existence of a unique solution for this kind of problem, an nth order differential equation. Here's what it is, for what it's worth. Okay, let a sub n of x, okay, a sub n minus 1 of x, a sub n minus 2 of x, all the way down to a sub 2 of x, a sub 1 of x, a sub 0 of x, okay? And the g of x. So all these functions of x, these coefficient functions of x that you have, and that last g of x, all those coefficient functions and those all have to be continuous. Okay? Not only continuous on an interval. Okay? And here's the only other thing. The a sub n of x cannot equal 0. Okay? Any guesses why the a sub n of x can't be 0? Anybody? If that were 0, this term would be 0. And then it wouldn't be an nth order differential equation. It would be an n minus 1 order differential equation. So for this to be an nth order differential equation, that one can't be 0. Okay? Any of the others can't. Okay? All the others could be, but this one can't. Okay? It can be 1, it can be -3, it can be anything, but it can't be 0. The others can be anything. Okay? Just a moment.
The next one would be an n minus 1, so just be a to the 0?
No, it could be anything.
Okay.
It could be anything. It's just the first one can't be 0. Okay? So, and this is for every x in the interval. For every x in the interval I. Okay? Now, next, if x equal x0, that initial value, okay, is any point in the interval I'm just going to say in I, the interval I, then a solution. Now that's all the givens. Here's the result. A solution y of x of the initial value problem given up here, okay, exists, okay, on that interval and is unique. Okay. Now, that's a lot of writing and a lot of blah, 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 just to get to the point of how do you know there is a solution? With all those coefficient functions, functions of x alone, okay, all those coefficient functions and the g of x are continuous, okay, on the interval, and of course that a sub n can't be 0, for every x in I. Okay, that means that none of those can have any gaps. They can't have any missing values or anything else. They have to be true for every x in the interval I. And if that x equal x0 is any point in I, in other words, this point here has to be also in the interval I, then the solution does exist and it is your unique solution. Now, are we ever going to go back and say, we're going to use this? Seldom, okay? But this first example will be one. Do we have time for it?
We have 5 minutes.
5 minutes. I think we might. Let's see if we can. If not, we'll pick it up next time, okay? So here's example 1. Here's an initial value problem. 3y triple prime plus 5y double prime minus y prime plus 7y is equal to 0. Okay? Now you tell me how many initial conditions we need.
4.
Not 4, up to the degree 3. Y of 1 has got to be, and they tell us here, happens to be 0. It doesn't have to be, but they just, okay. Y prime of 1. Now here's the deal. These initial conditions have to be at the same x value. In this case, it's 1. Once you saw the first one, you know they all have to be. Now, they don't all have to have the same y values. These just happen to have them. And you go up to y double prime. Never y triple prime, just to the next to the last one, and this at 1 equals 0. Okay? Now, that possesses, by the way, a trivial solution. Y is equal to 0. Because if y is equal to 0, then this term is equal to 0. The first derivative of 0 is 0. The second derivative of 0 is 0. The third derivative of 0 is 0. All those added together give you 0. And y at 1, if y is equal to 0, then y of any value is going to be 0. So all those are, yeah, that's a trivial solution. So there is a unique solution. Guess what? That is the only solution. Don't go looking for any others. Because you know the trivial solution works. This fits all the characteristics. This is continuous, that's continuous, that's continuous, that's continuous. Okay? Everything's hypothetic here. So since you know the trivial solution works, don't bother looking for any others. You won't find any. Okay? So that made it a pretty easy problem. It possesses the trivial solution at y is equal to 0, because that works. You can just look at it and tell that it works. And because the third order differential equation is linear, right? That's one thing. Constant coefficients, that means all the coefficients are constant, are continuous, okay? And all the conditions of that previous theorem are fulfilled. Therefore, that's the only solution on the interval containing 1, x equal 1. Okay? So don't bother looking for any others. So that theorem might save you a lot of effort sometime. Okay. Now, don't think we have time for example 2, do we?
1043.
Huh?
1043.
43. Don't think we do. So we're going to pick up next time with example 2. I really don't think we got far enough for any new homework exercises here. Let me just take a glance back here and see. This is a fairly long section, by the way. Well, not too bad. No. We didn't get far enough along, I don't think, for that to be the case. So, we'll pick up then with example 2 next time. All right. And this will pick up a little bit faster than some of the other sections. Sometimes I have a whole section of nothing but terminology, and it's so boring. This one, we've just about hit most of our terminology. A little bit more, but not too much. See you Thursday.
See you Thursday.
And maybe some of you on Wednesday. Okay.
See you.
Maybe. Yeah.
I won't be here next Tuesday.
Okay.
I have to make an appointment with my wife, so I'm going to be doing that. And I probably won't be done in time for me to make it back.
Okay. All right. Well, hopefully record everything.
Yes, sir.
Okay. Good deal. Thanks for telling me.